So where does all that energy come from? So we've got uranium-235 nuclide being hit with a neutron, and that produces a barium-140 and krypton-93 and 3 neutrons. So let's look at the mass of the reactants in the products. We learned in Chem 1A that in a chemical reaction, mass is conserved. The mass of the reactants equals the mass of the products. And you'll notice these masses have a lot of decimal places. These are very precise masses. So uranium-235 nuclide, 235.0439 atomic mass units. There's the neutron. It's approximately 1 atomic mass unit, but here we're going to use all the numbers that we know. So we add those together, we get 236.05258. We look at the mass of the products. We've got the barium, the krypton, and 3 neutrons. We add that up, we get 235.86769. Now, if we did an experiment in the lab by students and your products were 235.9 versus the reactants of 236.1, we say, good job, right? Good job. But these are measured out to the 5th decimal place. This is where the uncertainty is, right? Here we see there's difference in the ones place. These numbers are not the same. The products weigh less than the reactants. What happened to that mass? It was converted into energy. So in nuclear reactions, matter can be converted into energy. Mass is not conserved in a nuclear reaction. So this is where Einstein's famous equation comes in. E equals mc squared. So E is the energy produced, m is the mass that is lost, and c is the speed of light. So let's calculate the energy produced in the fission of 1 uranium-235 nuclide. I don't think I put numbers here. No, I didn't. So we'll have to go back and get them. Well, let's do the math here. So we got this guy, minus 235.86769. $236.05258 minus 235.86769. 0.18489 atomic mass units. So that is the amount of mass that's lost. So now we can go to our next slide here, and we just calculated the mass. So the mass is 0.18489 atomic mass units. The speed of light, anybody remember what that is? 3.00 times 10 to the 8th meters per second. If we want our energy to be in a recognizable unit, we can't use atomic mass units. So we've seen how like joules and coulombs and amps and volts and all these things are, all these different units are related to each other. They're related to each other through base units. And so the base unit for mass is the kilogram. So we need this to be in kilograms. We're gonna square this, so that's gonna get us meters squared per second squared. And if we get this into kilograms, kilograms meters squared per second square is a joule. So that's what the units need to be. Okay, so we have to convert atomic mass units into kilograms. Well, let's go to grams. Yeah, let's go to grams first. Does anybody remember what the definition of an atomic mass unit is? It's the if you take 12, a carbon-12 atom that has 6 protons and 6 neutrons, has an atomic mass of 12. So I did not get enough sleep last night. So if I remember correctly, Avogadro's number of atomic mass units is equal to 1 gram. The mass of a mole of things in grams is equal to the mass of one of those things in atomic mass units. And then kilograms to grams. The prefix kilo means 10 to the 3. So 1 kilogram is 1 times 10 to the 3rd grams. Okay, so we'll take our atomic mass units and divide by Avogadro's number. And then divide by 1,000. .07024 times 10 to the minus 28 kilograms. So energy is equal to mass times the speed of light squared. 3.07024 times 10 to the minus 28 kilograms times 3.00 times 10 to the 8th meters per second squared. So 2.76 times 10 to the minus 11th joules. Any questions? Yeah.
I have a question related to, when you were saying uranium-235 from part of the nucleus, exactly how do they work? I might have missed it.
How do they enrich it?
Yeah, is it like a
I don't know.
specific?
So are you asking how do they get?
How do they turn it to 236?
Okay, so uranium-235 is naturally occurring. Uranium-238 is also naturally occurring. Most of the uranium is uranium-238. It has some uranium-235 in it. And so what they have to do is they have to take that and separate the 235 and the 238. I don't know exactly how they do that. It's not a simple process.
I was just curious of like what elements they would use.
Well, they're not going to convert the 238 into 235. They're just going to separate it so that they can get more 235 in the sample. And they're not even going to get pure 235. They don't even want that because that could easily detonate, and nobody wants that. But when they talk about enriched uranium, and we're worried about this country that has enriched uranium, even though they signed a treaty that said they weren't going to keep any, we're concerned because they could use that potentially to create a nuclear weapon, right? Just regular uranium can't be used that way. Does that answer your question a little bit? Yeah. Any other questions? Yeah.
Yeah, Miss K, you put that the math was 0.18489, right? Where did you get that value from?
This one?
Yeah.
Okay, I got that from this slide. So I took the mass of the reactants and I subtracted the mass of the products. And so that was the amount of mass that disappeared. It's the mass that was converted into energy. Great question. Any other questions? So let's think about putting together helium-4, the nucleus, from its components. So helium-4 atom has 2 protons and 2 neutrons. A hydrogen nucleus is a proton, right? So 2 protons, this mass, 2 neutrons, this adds up to this total mass. The actual mass of a helium-4 nucleus, though, is 4.00260. It's less than this. And so the actual atom has less mass than the sum of the masses of its components. This is called the mass defect. It's like it shouldn't happen, right? You add up the pieces, and that should equal the whole thing. But no, the whole thing weighs a little less than the sum of its components. This is a mass defect. It exists in all stable nuclei. The energy that corresponds to that mass defect is called the nuclear binding energy. So that's the amount of energy that you would need to expend to break apart the nucleus into its component nucleons. Nuclear physicists often use the electron volt to report energy instead of joules or kilojoules or something. So the electron volt, lowercase e, capital V, is the kinetic energy of an electron that has accelerated through a potential difference of 1 volt. That sounds like a physics thing, doesn't it? So 1 mega electron volt, 10 to the 6 electron volts, is equal to 1.602 times 10 to the minus 13 joules, which gives us the result that 1 atomic mass unit is equal to 931.5 mega electron volts. So this is a useful conversion factor. You do not need to memorize that. So 1 atomic mass unit of mass is equivalent to 931.5 mega electron volts, which would be this number of joules times 931.5. So the mass defect for helium-4 is 0.03038 atomic mass units. We get that by taking the reactants here, subtracting the products, and that's the difference. This is the amount of mass that disappeared, that's missing. So what's the nuclear binding energy? Well, we just learned that one atomic mass unit is 931.5 mega electron volts. So this is a relationship between mass and energy. Here we have the defect in atomic mass units. We don't need to do what we did in the first example where we convert atomic mass units to grams and kilograms, and then we use Einstein's equation, and then we get an answer in joules. Because here, if they're asking for the answer in mega electron volts, then we'll have to convert back, right? So all we need to do is we need to take the mass in atomic mass units and use this conversion vector. So we put mega electron, oops, not milli, mega electron volts on top and atomic mass units on the bottom. 931.5 to 1, 0.03038 times 931.5. 28 point, so we got 4 sig figs. 29897. So that would be 28.30 mega electron volts. Now, is that a unit that's very useful in terms of calculating heat that's given off or anything? Not really. But there's the relationship on the previous slide between mega electron volts and joules, and so it can be converted. This is just a much easier way to convert mass to energy. You don't have to use Avogadro's number and make your brain hurt. So this is the binding energy for a helium-4 nuclide. We will often look at the binding energy per nucleon, and that allows us to compare different nuclides. Because helium-4 is a small nuclide. It only has 4 nucleons, 2 protons, 2 neutrons. And if you're comparing it with the mass defect in something like, bismuth, well, bismuth is going to have a much larger mass defect just because it's got a lot more particles. So we'll often look at the ratio of binding energy to nucleons, and a larger binding energy per nucleon is going to be a more stable nuclide. Calculate the mass defect and nuclear binding energy per nucleon in mega electron volts for uranium-238, which has a mass of 238.050784. And no, that would be too easy. So what do we need here? We need to calculate the mass of the components of a uranium-238 nucleus. So we need to know how many protons and how many neutrons there are, and then we need to know the mass of each of those things. So uranium-238. So that's the mass number, and it has 92 protons. So we can calculate the number of neutrons. 238 minus 92. 146. So we have 146 neutrons and 92 protons. So we need to know how many atomic mass units per neutron And how many atomic mass units per proton? It's approximately 1, but we need to be more precise than that. So we're going to go back and look. So here we have the mass of a proton, 0.00783, and the neutron is 1.00866. So neutron 1.00866 atomic mass units. And the proton 1.00783. Those are not numbers you need to memorize. Okay, so we've got 1.00866 times 146. 147.26436 atomic mass units. And then we have 1.00783 times 92. 92.72036 atomic mass units. For keeping track of sig figs, number of neutrons and number of protons those are exact numbers because we're counting. You can't have half of a proton. You've got 92 or 93. So we're looking at sig figs here. We've got 5 decimal places plus 1, so 6 sig figs. So that's going to be here and here. So we'll add those together. And get 239.98. That's not an 8. 98472 atomic mass units. Adding, we're going by decimal places, so we got 3 decimal places there. This is the mass of the components of a uranium-238 nucleus. We found the number of protons multiplied by their mass, number of neutrons multiplied by their mass, add them together. This is the actual mass of the nuclide. So we need to find the mass defect, which is the difference. Actually, let's just do it down here and avoid more writing. So I'm going to subtract the 238.050784. .933.936 atomic mass units. Any questions? The math here is very straightforward, but you have to remember what to do, right? How to think about it. We need to find the mass of all the pieces that went into making a uranium-238 nucleus and compare that to the actual mass to see what the mass defect is. It's the difference. So now we can take this and multiply by our conversion factor 931.5 mega electron volts per atomic mass unit. (1801). See, we're going to have 4 sig figs for 6 mega electron volts. So the mass defect is 1.934 atomic mass units. the nuclear binding energy per nucleon, we find that equivalent in energy and we divide by the number of nucleons. So 18, 1.46 mega electron volts. How many nucleons does a uranium-238 nuclide have? It's the mass number. Nucleons are protons and neutrons. All the residents of the nucleus. You know, like Klingons, nucleons, right? So we've got 138. It's this guy right here. So, sorry, 238 nucleons. Let's spell that correctly. So 7.569 mega electron volts per nucleon. Oops. Nice. Any questions? I can pretty much promise you there'll be a question like this on the exam. A common mistake, something that students overlook, is if it's asking you for nuclear binding energy per nucleon, you have to take that extra step and divide by the number of nucleons. And so in problems like that, this is one of the most common mistakes I make, is that the student will just report this number. So watch out for that. Make sure I didn't skip anything. So that was the nuclear binding energy per nucleon for uranium-235. Right, it was about 7.6. So that's this guy, or close to that guy. And so that's just below 8. So here what they've done is they've looked at the nuclear binding energy, the binding energy per nucleon versus the mass number. And we see that for H2, this is deuterium, is hydrogen with 1 neutron when it normally doesn't have any neutrons. And this is tritium. No, I'm sorry, that's helium. But this is down around 1 mega electron volt per nucleon. And as we increase in mass, we see an increase in the binding energy per nucleon. And there's this guy here, the helium nucleus is going sort of out of order. That one has a lot of energy. But this hits a maximum at atomic number 60. Which one is atomic number 60? That's neodymium. So if we take heavy nuclei and break them into lighter ones, the reaction is going to be, or the result will be exothermic. Because if I take this and split it into 2 parts, the 2 parts will have lower energy per nucleon. And so we'll get energy released. That energy has to go somewhere. If we combine 2 light nuclei into a heavier nucleus, that is also exothermic. Man, I'm just finding typos all over the place. Is also be exothermic. How many years have I used these slides?